Okay, the night skies of Catron County. We're lucky we live in one of the best dark sky sites in the world, and I'll show you why. Okay, reasons why it's so good. We're at high altitude. A lot of us are over 7,000 feet. There's no light pollution. We don't live near any big cities that are going to create a light dome in the sky and block out the lights. The majority of our nights are cloudless. Most of the weather's good, and we are away from the jet stream, which is much further north, and it's very dry here, so there's little atmospheric moisture up in the upper atmosphere. So altitude, it's important because the higher we are, the closer we are to the sky, even though it's a little bit, but it's less atmosphere to look through. And you can see where we're at, where the jet stream is, and the jet stream creates a lot of turbulence in the upper atmosphere, which makes things, you know, when you look up and you see stars twinkling and that kind of stuff, that's all related. Some of the challenges to astronomy here. This is a single exposure, and those are airplanes and satellites and one meteor. One meteor. Where is this? Can you see this? I can't see this thing.
The laser doesn't shine on the screen.
Wow, it does not shine on the screen. Okay, so this is the only meteor in the picture. That one streak in the middle. And a nice picture, otherwise a nice picture of the Milky Way. And also you can see at the bottom this glow is from city light pollution somewhere. Okay, this is the Bortle scale. So this is a scale of measurements as to sky brightness. Most of it caused by light pollution in cities. So you can see here that would be like Los Angeles or New York. You're not going to see anything except the glow. And then we go, I think Albuquerque is probably here at this point. It used to be over, it actually used to be over here, but now that they've been using LED lighting for everything, it's so much more powerful as far as blocking out the light. And you can see where we're at. This is a light pollution map. And you can see how lucky we are. If we were in the East Coast, good luck. But where we're at, and you can see this dark spot is literally where we're at now. It's very dark, and we're lucky. Okay, this is what I was talking about with LEDs lights. So this is a galaxy image from a dark sky site versus a city, and I would say nowadays, that's an older picture. Nowadays, that right frame would be white. You wouldn't see any detail at all. This over here on the upper right is the spectral emission from common human light sources like sodium vapor, mercury vapor, you know, the old school street lights and things like that. They had discrete bandwidth that you could filter out at one time. You could actually get filters for your cameras, and you could block those bright sources of light and then get everything else. But we can't do that anymore because this is the spectrum of an LED light, and it is wall to wall, and unfortunately it's really heavy in the blue. And the problem with that is, the same reason the sky is blue, is all the particulates in the atmosphere are reactive to the blue spectrum of light and reflect. And so if you're shining blue light up there, it's going to react with all the particulates in the atmosphere and reflect and block your view. So warm lighting would be better, but they don't do that. Here's an example of objects that can ruin your long exposures. So on the upper left is a nice picture of a comet and a bunch of Starlink satellites.
Wow.
Yeah. And the longer the exposure, the more you're going to get. The upper right is an airliner passing through a frame. And then there's a wide field view with all sorts of satellites and things.
How long was the first one?
This one, probably about 5 minutes. This is a 30-second exposure out here with an all-sky camera. It's a little tiny camera with a fisheye lens that's just pointed straight up all the time. And you can see how clear the Milky Way is, 30 seconds. And then that streak is an asteroid, a space rock, a meteorite. Astrophotography. We could set up a camera and take an exposure all night if your telescope is tracking the object perfectly without any problems with the gears or anything. Nothing gets bumped. You could take a long exposure all night long, but what's going to happen is nothing's perfect. This telescope's not going to track perfectly for that long because of errors in the gears or wind or an airplane flying through the frame or numerous satellites or whatever. So what we do is we take a bunch of exposures throughout the night, and sometimes over many nights. So you get a target, you start taking pictures of it, and I typically will take maybe 5-minute exposures, 2-minute exposures, depending on which telescope I'm using. And you take a whole bunch of exposures that night, and then you calibrate them to dark. You take dark exposures with the camera covered, and so any noise that's in the sensor or bad pixels or whatever get weeded out. And then you go through all those exposures and you find the ones that you don't want, that had an airplane or a satellite or whatever going through it, and you get rid of them. And then you stack them. And stacking is what they used to do in the old observatories with film cameras, is they would expose on glass plates. And then they would take those glass plates and they would stack them on top of each other and then shine a light through them and then photograph that. And that would eliminate some of the noise and strengthen the signal that they were getting. Because if something actually existed in the frame, then it would exist in all the frames. If it was just an anomaly, it would only exist in one frame, so it would be weak. So you strengthen the actual signal and reduce the noise. Here's my old observatory. This arrangement we called the Sydney Opera House. It was a giant convertible, like from an old timey car, and you would pull it over, and the tarp would protect the equipment. Okay, this is filtering. This is your narrow band, and we have filters. So you would have a camera that is a black and white camera, and you would take a picture of your target with a red filter, and you take your picture of the same target with a green filter and a blue filter, and you put those together and you get a full color image. And also what we do, oops, let me go back. And also what we do is I have other filters in here. So I have red, green, blue, and then I have a hydrogen alpha filter, which is the emissions from hydrogen gas, an oxygen 3 filter, and a sulfur filter, which are the 3 primary gases that fluoresce in nebulas and things. And so this picture on the picture on the right and left are the same target. This is what your eye would see if you were sensitive enough to see all the colors. That's natural color over on the right. This is filtered. This is the colors that if you could see hydrogen and oxygen and sulfur, you would get this color. So here's what hydrogen alpha looks like through a black and white camera with that filter, and oxygen and sulfur, and you can see they're very different. And then you put them together and you get a neat color image, and this is what the Hubble does. They have the same type of filters in the Space Telescope. And here's an explanation of stacking. So you see the first image over here is very noisy and granular and things like that, but the other image looks a lot better. So what you do is you stack all these exposures that you took all through the night and it amplifies the signal, what actually is there, and gets rid of all the stuff that is transient, like noise, and eliminates that. And in planetary, instead of taking long exposures, we take very short exposures, like video, essentially, high-speed video. And nowadays we have these cameras that were developed for machine vision for factories and things that can see, the products just going across the line and read the serial numbers as they go by, even though it's it's a blur. So these cameras have a very high frame rate. So you can see the first frame of Jupiter, one frame, it's very, very noisy. And you progressively, as you stack more frames, you get a really sharp image. That's 1,000 frames. Typically, when I take a picture of Jupiter, I'm running about 10,000 frames to stack.
Your microphone's
Yeah, it
dropping
keeps
out.
cutting out. And here's Saturn, and you see how bad that one frame is as opposed to a stack of 6,000 frames. Here is the Seagull Nebula after stacking and before optimizing it in Photoshop to bring out all the colors and things like that. Okay, this is why we stack, especially with the video of the planets. Looking up through the atmosphere is like being in the bottom of a swimming pool and seeing it, because of the difference between the atmosphere and no atmosphere. It warps. And so what we do is we're running high-speed camera on your planet so fast that every once in a while the atmosphere will be perfectly clear, and that image got captured, and then the rest of them are all muddy. And so you have software that goes through there and can identify which is clear and which is not clear, and reject all the not clear, distorted ones, and then only stack the sharp ones. Okay, this is a slideshow of astrophotos that have been taken here, about 8 miles from here. So that is several nights of the Crescent Nebula in hydrogen alpha and oxygen 3. So 2 frequencies of light. This picture makes me happy. This is my best picture that I've done of Jupiter. And this was like about 2 weeks ago.
2 weeks.
And I was lucky enough to get the shadow of Ganymede on the surface of Jupiter, and actually some detail on the moons, Callisto and Io. And Ganymede and Callisto, these moons are almost the size of Mars. They're really big. They're very big moons. But Jupiter's a very big planet. Medusa Nebula. That is in full color with the addition of, that's 2 telescopes. One telescope taking full color like we would see, and one telescope taking oxygen and hydrogen, and then all of that information combined. This is a galaxy, much like ours, and seen on the edge. This is a wide view of many objects. There's a Sharpless catalog, a person named Sharpless, who went through back in the day and cataloged all these different objects. And there's a bunch of them in there. The top one is called the Lobster Claw Nebula. You need to get in here. This is Comet Lemon. This was the brighter of the comets that came out this year. This is a comet from our solar system. I think it's got like, I don't know, an 80,000 year period, so we won't see it for a while. But it came from our solar system and went around the sun and on its way back out. And the comet that the news is sensationalizing and saying, it's space aliens or the mothership or whatever. It is a comet. It's not a comet from our solar system. It's a comet from another solar system in our galaxy. We don't know which one, but we can tell that it's a comet because of how it behaves and what it's made out of. But we can tell it came from somewhere else by the trajectory that it came into the solar system and the speed. And also the composition is quite different from the composition of comets from our solar system. This is the spider.
Pictures of that one? Did you capture any of that?
I did.
That was.
This is the Spider and Fly Nebula. And if you turn it clockwise, it kind of looks like a flamingo.
Everybody turn your head to the left.
This is one of my favorites. This is the Flaming Star Nebula. And these bright, bright stars in the middle are much bigger than our sun, and they put out a lot more ultraviolet radiation. And the ultraviolet radiation is what lights up the gases. They fluoresce. So your fluorescent bulbs are glass tubes with an electrical high voltage plasma running through them, which creates ultraviolet light. And the glass tubes are coated with a certain material that fluoresces from the ultraviolet light. And that's what's happening here, is this gas is lighting up in response to being bombarded with ultraviolet light from those stars. This is one of my favorites. This is the Chinese Dragon Nebula. So many colors, and this is an emission nebula that is lit up by the ultraviolet from the stars. Thor's helmet kind of looks like a helmet. A lot of these don't actually have names; they just have numbers. So it's up to people to come up with a name, I guess. This is a bunch of galaxies, so this is Caldwell 23, and I had a picture of that earlier, close up, and a bunch of galaxies in that picture, all different kinds. Everybody recognizes the horse head and the Flame Nebula. Those are in Orion, which is starting to come up at night now after dark. Do you remember what Orion looks like? This is the Small Rosette Nebula. I like dark nebulas. This is a dark nebula. This is very, very many long exposures during a new moon when there's no moon in the sky and there's no light pollution or anything. And these clouds you would not even see with your eyes, but this is dust and stuff left over from the formation of the galaxy. And it's literally dirt. But these structures are so huge that entire solar systems, like our solar system, are being formed in them. They're massive and far away. This is the Ghost Nebula. You see the little ghosts in the middle? This is the Bubble Nebula. It looks like a bubble, because it is. It's a bubble of gas expanding from a star that underwent its death and expanded. This is another dark nebula and it's just literally dirt with some hydrogen gas, clouds of hydrogen gas. The Wizard Nebula. They're so pretty, and there's so many of them. The jellyfish. Like I said, some of them have names. Most of them have numbers. Okay, this I did the other night. This is the Perseus cluster of galaxies. And I'll point it out later when we're talking about the size of the universe. But there is, in this picture, there are thousands of galaxies. I mean, any stars that you see in this picture, little tiny stars, those are within our galaxy. And we're looking out past that. And all these galaxies are in open space, long, far beyond our galaxy. Millions and millions and millions of light years away. That one they call the Christmas tree nebula. If you turn it, it looks more like a Christmas tree.
Can you explain why some of the names describe things that are absolutely not visible to us from your pictures?
Okay, here's the lobster. I'll get to a couple that are like that. Okay, this is the Propeller Nebula. So what she's talking about is when a lot of these were named, people would look through their telescopes and they would only see the brightest part of the image. And so the brightest part would have that can pick up all this other light. So you can barely see this propeller. Do you see it? You can barely see it because that is the brightest part of the image. And like I said, if you were looking at it through a big telescope with your eye, you would probably see that S-shaped propeller, and that's how it got its name. But now that we can get so much more information, it kind of minimizes the main feature of it. This one's called the tadpoles because there's these little structures here that kind of look like tadpoles. These are planetary nebulas. So the difference between this nebula and a planetary nebula is that these nebulas are gigantic, mind-bogglingly huge structures of gas and dust and things where stars are born and solar systems are formed. But then you go to a planetary nebula, and this is where a star has died. And so our sun, when it expands and dies, it'll end up looking something like this. And you can see in the center of these there's a little dot, and that's the core of the star that made it, and all its layers sloughed off. This is the Rosette Nebula. I think it looks like a skull.
Yeah, it does.
So this is the Rosette Nebula taken with regular color, like what you would see with your eye. And this is the Rosette Nebula taken in hydrogen, sulfur, and oxygen. And you can see it's pretty much the same, except you can see different features in the structure clearly.
How many?
And you can tell what
How
kind
many photographs of this did you have to put together to make this?
This one, a lot more than that one. So hundreds and hundreds, like, I don't know, maybe 500 for this one. So I had to take a bunch in the sulfur and a bunch in the hydrogen and a bunch in the oxygen and then combine them to get the full color image. The sun. So this has been an interest of mine lately because at night it's been cloudy, so I've been taking pictures of the sun. So I have a special arrangement that is a spectroheliograph, and this is how you would see the sun if you looked at it through a telescope with a filter so that you didn't burn your eyes out, because you would. And this is how you would see the sun if you looked through a device that only showed you the hydrogen alpha gas, which is the same gas we see in some of those structures. And the way I take pictures with this is I don't take a picture of the whole disk at once. I have the telescope has a spectroheliograph which has the light comes in from the telescope through a slit, and the slit is microscopic. And then that light goes and it hits a diffraction grating, which is like a hologram. And it splits the light into all its frequencies, and then it sends it onto the camera. And the camera is only looking at one of the frequencies of light, and in this case it's hydrogen. And so I can see all these structures on the sun.
What are those structures?
So these are prominences. These are where your ejections come out of, and all these white things are above the surface of the sun. And you know, all these dark spots here that you see, that's where the magnetic fields of the sun are converging, and also they erupt and they give us the auroras that we had the other night when that mass gets ejected from the sun towards us. These are some of the different frequencies of the sun that you can image using a spectroheliograph. You can separate the different kinds of light. This corner where it says solar continuum, that is white light that we would see through a filter, and the rest of it is discrete narrowband frequencies. Okay, this is where we get the auroras. So we've got the sun, and we're in the middle of cycle 25. This is every 11 years the sun goes through a cycle of high activity, low activity. And we've been measuring it for long enough that this is the 25th cycle that we've been measuring, and of the 11-year cycle. And right now we're in the middle of the height of the 25th solar cycle, and we've had a couple of auroras in the last couple of years, all the way down here where we normally don't see auroras at all. People way up north see them a lot, but we don't. So the Earth has a magnetic field, and the reason the Earth still has an atmosphere and has water and things like that is because it has a magnetic field. It's weak compared to our magnets, you know, our strong magnets, but it's strong enough over the whole surface of the Earth that it can block some of the solar radiation that is hitting us, and it protects us. It directs it away from the Earth. So you see these little auroral ovals, and you see the shape of the magnetic field of the Earth. They direct those charged particles that are coming from the sun down into the northern and southern areas, poles of the globe. They're following the magnetic field, and they interact with the gases that are in our atmosphere, like oxygen and hydrogen and nitrogen and things like that. And that's what gives us the different colors.
Lee did not take this picture.
What?
I said you didn't take that picture that you just showed.
No, I didn't take this picture. And Mars doesn't have a magnetic field anymore. Something happened to Mars. I guess it solidified inside, and there's no longer any churning magma or metals, and so it doesn't have a magnetic field. And so the solar wind that's constantly streaming from the sun has stripped most of the atmosphere and water away. This is a picture from the ISS of aurora going on. This is a picture from here on November 12th, the first night that we had the crazy auroras. I took that with my cell phone.
Wow.
That's how bright it
The
was.
sky really looked like that. It wasn't
Yeah.
quite that intense to the
It was
eye.
amazing. Yeah,
But
you were
the
just
sky
going
was
outside
red.
and you were just like, wow, is this real? And there were some different colors involved, mostly red because we're so far south. But yeah, it was amazing. Here's a video of the next night. If I'd had my camera set up the first night, the video would have been much better. But this is the second night, so we got two. We actually had 3 coronal mass ejections that happened in fast succession. The first 2 we got to see the first and second night. The next one was in the middle of the day, so we didn't see anything, but it did affect satellites and communications and things like that. got some of the green. It was cool. Where are we? We are tiny. And it goes both directions. It goes from us down to the tiniest constituents of matter, and then up the other way into the vastness of the universe. Here is a not to scale diagram of the solar system that we live in. And you've got 8 planets because they demoted Pluto. Earth and Mars are in a really good spot where life could exist because of the energy from the sun. We're just right in they call it the Goldilocks zone. Here's a scale size comparison of our planets. And you can see how much bigger Jupiter is to Earth. And you look at Mars down there, and some of the moons of Jupiter are as big as Mars. They're planet-sized. All right, this is a larger diagram of the scale of the solar system. So right here in the middle, here's our sun, and here's Mercury, Venus, Earth. Then we've got the larger planets, the gas planets, and then Pluto way out there. And Pluto is, there's a misspelling here, that's belt. Pluto is way out in the Kuiper belt, where we have discovered the reason they demoted Pluto from planet status is we've discovered a whole bunch of planets that size that are rocky ice balls that, you know, if we would have too many. I guess it was a decision they didn't want to name all these little mini planets, but there's so many of them. And then of course this disk is that disk down there in the center. Then we have the Oort cloud, which is huge, and this is all the remnants of the building of the solar system itself. After all the planets swept up all the debris and everything and became planets, this is all the leftover cloud of stuff. And that's where comets come from. So when you see a comet, it came from way out there.
Does that turn into a dark nebula over time? Does it become one of those drifting dirt things?
It's dust and water. Water is one of the most plentiful substances in the entire universe. You wouldn't want for water if you were living in space and you had a way of getting around, because water is everywhere. Hydrogen and oxygen are the main constituents of the universe, and they make water. So all the comets come from the Oort cloud, and you see this 5,000 to 100,000 AU in diameter. AU stands for astronomical unit, which is equal to the distance from the Earth to the Sun, average. So it's pretty big.
Where's Voyager 1?
What?
Is Voyager 1 in the Oort cloud, or is it past the Oort cloud?
Past. Yeah, it's left.
Past the Oort cloud.
Yep. Yeah, it's taken, what, 50 years? It's just going. What is a light year? Light speed is slow. We think of light speed as fast, but there are cameras now that you can see a laser beam, and they can film it and they can slow it down, and you can see the light coming out, hitting something and bouncing off. I mean, it's slow. We think of light as fast, but when you look up at the sun, you're seeing the sun as it was 8 minutes ago. It took 8 whole minutes for the light from the sun to come all the way through space to your eye. So it's not that fast. Here's the Milky Way. The Milky Way, that's for the small text, I'm going to read it. The Milky Way and its neighbors is seen from a location about 700,000 light years from the sun.
Slow down.
The nearest galaxies are the 2 irregular dwarfs, the Magellanic Clouds. In the distance beyond them is the spiral galaxy M33. That's the Andromeda Galaxy, is their M31. There are about 30 members of the local group, and not all of them show up in this perspective. The location of our sun is marked by a red dot. In reality, it would be invisibly small from this distance, and you can see where we are, we're on the edge. So if you think of it like a big dinner plate of stars swirling around, it's flat, it's swirling around, it bulges in the middle. We're way out in the outskirts. Way out there, just like here. Way out in the outskirts. This is a picture of that Andromeda Galaxy. So this is a representation of our galaxy. Within the distance is the Andromeda Galaxy, which we are currently both heading towards each other, and will collide in about 5 billion years, so you don't have to worry about it. And the distances, you know, everything looks like it's close together, all these stars and everything, this glow. But actually, in reality, the gravity will tear the galaxies apart, kind of like in a blender. But there probably will be very little interaction between stars and planets. They won't like hit each other. It's just like two clouds coming together. Okay, if you want to really feel small, here's our solar system. It takes 10 light minutes for this perspective. So about Mars out to the sun, that's 10 light minutes across. Here's our nearby bright stars. That's 30 light years, so across in this picture.
So are those stars that we could see from here with the naked eye?
Oh yeah. They're
So
bright
that's
stars.
our night sky
Yeah.
in that second picture?
Right.
Okay.
The Orion spiral arm, which is where we're at in our galaxy, that's 1,000 light years across. This picture of the Milky Way galaxy, that scale line is about from the center of the galaxy out to the edge, 50,000 light years. So if you got on a spaceship that could travel at the speed of light, it would take you 100,000 years to go from one end to the other. But to you, on that spacecraft, it would be instantaneous. You would go from one end to the other, but you would find that 100,000 years had passed for everybody else. And then it gets into this web stuff. So all of these webs are made out of groups of galaxies. So I showed you that picture of the Perseus cluster, all those thousands of galaxies in that picture. That's a tiny speck. It's a tiny speck inside here. And gravity is what is holding all these galaxies into this web-like structure. And, you know, they talk about dark matter and dark energy, and I don't think that that's a thing. I don't think it exists. I think it's all explainable by gravitation. But there's two camps on that. And then, you know, it gets even bigger, and it just goes on and on and on. And when they say, you know, the universe is so big, a certain size, that is the part of the universe that we can see. We cannot see past a certain point because the universe is expanding. I know they say nothing can move faster than the speed of light, except space-time. The universe itself can expand faster than the speed of light. And it is. It's a bubble that's expanding. And so we can observe things out to the beginning of what we think is the beginning of the universe because of how long it took for the light to get to us. But that doesn't mean that there's not even more beyond that. That's just what we can see. So it's very big. We have no idea how big the universe is. And we won't know. Astronomy in Catron County. So everybody knows about the VLA. That is radio astronomy. And the electromagnetic spectrum is that. It's a spectrum from DC all the way up to voltage, up to microwaves and x-rays and all that kind of stuff. And with our eyes we can see this much of this, just a tiny little sliver. And so when you're looking at space with radio telescopes, it's just like you're looking at it with light. You're just shifting that frequency over into the radio band, and so you can map it to colors and things like that. And the more radio telescopes you have, the more resolution you have in detail. So you can see just like as if it was light, but it is a form of light. It's radio waves. People are building observatories out here. There's commercial observatories, there's government observatories, and private ones. Top of the World in Pie Town has a whole bunch of astronomers that live up there. But the first astronomers were Native Americans here in Catron County. We got cliff dwellings, all these places. They paid attention to the movement of the sun and the moon and the seasons, and they could tell by shadows and watching the stars and where this constellation came up at what time of the year, when it was good to plant and when it was good to do all these different things. And they based their lives on the movement of the sky. Chaco Canyon is like that. It's aligned astronomically, and there's astronomical features and things like that. So it was a big part of their life, was paying attention to what was going on in the sky. They didn't have the internet, they didn't have TV, they didn't have all these distractions. They looked at the sky.
Well, where is it in Chaco Canyon where the light comes through the
sun dagger.
That's coming up. I will show you that in a couple slides. Okay, so this petroglyph is purported to show the supernova in 1054 AD that was documented by Chinese and Persian astronomers at that time. They observed it, they wrote it down, but at the same time, over here, these people also saw it. They saw this bright, bright star in the sky that had not been there before, and after a few weeks it went away. But they didn't know what it was. Well, we know that it is the Crab Nebula. If you take a picture of the Crab Nebula every few years, you can see the expansion of it slightly. So that is a planetary nebula, so that's a star that exploded, and that's the guts, that's spreading out. Here's the sun dagger you were talking about. So in Chaco Canyon, they have this, I guess you would call it an indicator that these people built, and they think this actually predates the structures at Chaco Canyon, big ceremonial structures. But somebody set this up, and it's very accurate where the arrow falls, depending on the time of the year, and so they knew when to plant and when to do all these things based on that. Somebody would watch that and say, look, the sun is in the middle of the thing, we've got to do this thing. Pretty neat. Took a long time to get that right, I'm sure. Any questions?
Yeah, where's Betelgeuse now? Isn't Betelgeuse like...
It's part of Orion. It's part of Orion. It's a supermassive red giant that is dying, and we may get to see it go supernova in our lifetimes. That will be pretty cool. It'll be bright.
And we got to just like a cave.
600 light years away.
How far away is the Crab Nebula from here?
I don't think the Crab Nebula is that far away. Let's see.
So it wouldn't be as dramatic as that, possibly.
It would be. Yeah, at night you would see it really bright. It would be like, it wouldn't be as big as the moon, but it would be bright like that. You could read it by it. It would be the bright star in the sky for a few days or weeks, and then it would fade away. And then we would have a neat planetary nebula to look at and watch expand over the years. Yeah.
What about 3i Atlas? Did you show any?
I didn't put a picture on there of it. So the pictures I got were early, and so it was just a green light, And now it's starting to come up in the morning where I can get pictures of it with the tail and everything. But yeah, it's.
Are you gonna post those on your Facebook?
I will. Well, I don't use Facebook anymore, but.
Where will they be?
She can post it on Facebook.
I can.
I'll give them to her.
Yep, I could probably get it up on the Historical Society.
Oh, that'd be cool.
Yeah.
Yeah.
What about the other one that's golden, the Atlas, K1 Atlas, 2025 K1 Atlas is actually golden?
A little bit, but they're mostly green because they're all made of the same stuff. They're all made out of water and rock and different metals and stuff like that. So they're pretty much all the same color. They're mostly green. The difference between Atlas was it had a lot more nickel in it than most of the comets that we have in our solar system. It just depends on how that solar system evolved, the kind of star it has. We have no idea because it came from really far away, but the composition is a bit different. But mechanically, it's the same thing. It's a ball of water and ice and metals, and as it gets nearer the sun, it warms up, and it starts outgassing, and it leaves a trail behind it as it goes, and it also, as it warms up, it's melting, and all the gases are coming out, and it flares up, and it gets really bright. And the trail that a comet leaves behind it as it goes through the solar system is chunks of rock and things that are left as it's coming apart because it's melting as it gets nearer the sun. And every time the Earth in its orbit passes through one of those comet trails, that's when you get a meteor shower, because that's all the little pieces of rock that were left behind from a comet. And that's how we know that this meteor shower is going to be this date every year, because that's when the Earth passes through its path.
Like, I've heard that it was headed towards a Scorpio now, and like, where did it come from though? Did they say, did they approximate where?
Somewhere in our galaxy. I mean, we can't tell how far it came or what, but we can tell the direction it came. And it came into the solar system, and the sun's gravity started pulling it more and more, and then it slings it around and it goes out somewhere else, which is what happened with the one 3 years ago. Oumuamua, yeah, same thing. And people were like, well, it changed course. Yeah, it changed course because it came into the sun's gravity. And
so you just count like what Avi Loeb, what he's saying from Harvard?
so the media is presenting what Avi Loeb says as something sensational, but if you really listen to what he's saying keep an open mind. Because, we look at something and we say, oh, that's a comet. We look at this and say, oh, that's an asteroid, this and that. He says, keep an open mind because we have sent space probes out. We've sent Voyager and things like that. So if you consider how big the universe is and how many galaxies there are, and even in our own galaxy, how many stars and planets there are, almost every star has planets. And so if you're talking about trillions of stars and multiple trillions of planets, the average is there's going to be some with life on it, some with civilizations. They probably don't look anything like us, but if they're smart and they know how to build things, maybe they're putting out space probes. So he's saying, maybe it's something, maybe not, but keep an open mind. Don't just dismiss it right away. It's a comet. That's all he's saying.
In the life of the universe, when do you think that may have first started to begin?
What's that?
In the life of the universe, when do you think that practice may have first started?
Oh, I don't know.
No
From the
estimate?
beginning, because it's all leftover stuff from solar system production. When you make a solar system, when it forms, there's a bunch of stuff left over, and the gravity starts pulling that stuff that's really far away in, from the Oort cloud, and it pulls it in, and it gets closer and closer. And when it's out there, it's pretty static. It's inert. It's frozen, hard frozen, negative 400 degree water that's frozen as hard as rock and metal. And as it gets closer to the sun, it warms up and it does things.
I just wondered, I think you answered it, but I always wondered what propels a comet. I mean, is it gravity?
Gravity, yeah. So these rocks of ice and dirt are way out there in the Oort cloud, leftover pieces, rubble from the solar system.
Somehow they gather up together?
and they bump together. Sometimes they bump together where they create their own gravity enough that they all clump and you get a planet, you get a small planet. Other times they bump and it knocks it closer where the sun's gravity can pull it a little bit. And the closer it gets, the more effect that sun's gravity, Jupiter's gravity, the whole of the solar system has a gravitational field, and so everything's going to want to go towards the center. And if it goes directly at the center, it goes right into the sun. But if it's coming in at an angle, the sun pulls it in, slingshots it out, and back out it goes. And this is how we get comet, like Halley's Comet, which is like every 86 years or whatever. We, like clockwork, we know when the comet's going to come back because its orbit takes it out so far and brings it back. It's a long elliptical orbit, like our Earth orbit is round. It goes around the sun once a year. These guys go way out and come back.
Well, I don't know, 20-some years ago, I lived in Austin, and there, we were watching the Hale-Bopp comet.
Yeah, Hale-Bopp.
Yeah, Hale-Bopp, something like
Yeah,
that.
yeah. We've had some good, decent comets that you could see.
The high Kentucky.
I wonder,
Huh?
wonder when that guy's coming. I wonder when that guy's coming back.
Some of them we won't be around for, you know. Some of them are.
Well, I know that, but
Yeah, we don't have any comets that are like a low periodicity, like a few years. They're all decades, because it's a long way to go out, a long way to come back.
Do you know when the next big one is?
We don't know. I don't know when the next big one is. Like, we've had a few discoveries lately that have been surprises. So there's still a chance that we might get nailed real good.
So how did your pictures come out? The last ones you took of Atlas?
So those were, the last ones I took were early on. So Atlas for a few weeks has been behind the sun.